Hi, hello everybody. Last class we have seen what tree is, different kinds of trees and some properties about trees. In today's class, given a graph, we'll define what is spanning tree of this particular graph. Spanning tree is nothing but a subgraph of the graph that is given to you, which has to be a tree, and it should span all the nodes of the graph. Equivalently saying, this spanning tree is nothing but a tree that is covering all nodes of the graph that is given to you. Then we will define what is a weighted graph. Given a graph, each edge can be assigned some weights. This is a practically, when you have to model any practical problem as a graph, you tend to give some weights to the edges according to the problem that you have got. And if you have got a weighted graph, that means a graph having weights for each of the edges, then there will be more than one spanning tree in that particular graph. Then the challenge is how to find the minimum spanning tree. We will see couple of algorithms, Kruskal and Prim's algorithm. Using these algorithms, we will find what is the minimum spanning tree of a given graph. First, weighted connected graph. It is simple. It's simply a graph in which so this is a graph, we all know that, but if weights are given to each edges, we call it a weighted graph. Suppose this is V1, V2, V3, V4. It is a graph of 4 vertices, V1, V2, V3, V4, and each edge is having a weight associated to it. And a spanning tree, as I told, is nothing but a tree of this particular graph, that means a subgraph of this particular graph which is not having any cycles in it, and it should cover all the nodes of this particular graph. What I mean here is, if I take V1, V2, V3, V4, is it a subgraph or not? Definitely it is a subgraph because its vertex set is subset of the vertex set of the graph that we have got, and its edge set is subset of the edge set of the graph that we have got. Hence it is definitely a subgraph. Let us see it is a tree or not. It is very much a tree because this particular subgraph is not having any cycles in it. There is no cycle in it. And let us examine whether it is a spanning tree or not. To check whether it is spanning tree or not, we have to see that all vertices of the graph that we have got should be covered in this particular tree. Yes, there are V1, V2, V3, V4 vertices are there in the graph that we have got, and all of them are there in our tree also. Hence it is qualified to be called, this particular subgraph, a spanning tree. I will take this particular another example. I will say V1, V2 and say V3. Is this a subgraph or not? This is very much a subgraph of this guy. This particular thing is a very much a subgraph of the original graph that we have got. But I ask you the question, is it a span? It is not, and this subgraph is not having any cycles in it. Hence it is a tree. There is no problem in calling this guy a tree But when I ask you the question, is it a spanning tree? No, it is not a spanning tree, because the vertex V4 is not being covered in this tree. It is not spanning the vertex V4. Hence, it is not a spanning tree. It is simply a tree. Now you got what it means by spanning tree. Now, cost of the spanning tree is defined as sum of the weights of all its edges. For example, we have seen this particular guy is a spanning tree. So it is having 2, 5, 9 as the weights of their edges. So the cost of the spanning tree is as simple as 2 plus 5 plus 9, the sum of costs of all of its edges, that is 16. The cost of this spanning tree is 16. Now the point is, given a graph like this, how many spanning trees are possible? Definitely there can be more than one. There will be n number of spanning trees given a graph. This graph is very simple. Even this graph is having lot of spanning trees. This is one spanning tree. If you want me to draw another spanning tree, I will draw it like this. This is V1, this is V2, this is V3, this is V4, and its costs are 8, 9, 5. The cost of this cost of this spanning tree is 17 plus 5, 22. This spanning tree cost is 22. This spanning tree's cost is 16. All are actually spanning trees of the same graph. It means to say that given a graph, there will be n number of spanning trees with their cost being different. Now the challenge is how to find out the spanning tree which is having minimum cost. That is called minimum spanning tree. It is having n number of applications. Most of the practical applications are like you have got a graph and it is sufficient for you to find minimum cost spanning tree, minimum spanning tree to solve the problem that you have got. Most of the real life problems can be modeled as an MST problems. So in this class, let us study how given a graph you can find minimum spanning tree. That is the agenda of this particular class. Okay, we will see couple of algorithms. First one is Kruskal algorithm and another one is Prim's algorithm. And as I told, there can be more than one minimum spanning tree. That means there can be two spanning trees which are having the cost as the same, and both of them can be a minimum spanning tree. That means minimum spanning trees are not unique. There can be couple of minimum spanning trees. Both of their cost is the same, but both are spanning trees, and their cost is definitely less than cost of any other spanning tree. So hence these two can be qualified to be minimum spanning trees. So you can have more than one minimum spanning tree for a given graph. Take this particular example, though I called it a network, don't worry, this is a graph actually. This graph has 10 edges, spanning tree. Now I'll ask you one thing. If you have got a connected graph, say obviously we'll talk for a connected graph only, all the spanning tree business. So you've got a connected graph, okay, and then a spanning tree will have how many edges? If you have got a graph of n vertices, the spanning tree will have how many edges inside it? Definitely n minus 1 edges, isn't it? Any tree will have n minus 1, any tree of n vertices will have n minus 1 edges, and you have got here a spanning tree of this particular graph we are talking. That means a spanning tree of this particular graph will be having all the number of vertices that are there in the original graph. So the spanning tree will have actually n number of vertices. given the fact that the original graph has got n vertices. Hence, because spanning tree has got n vertices, and by the very property of the tree, you will know that there are going to be n minus 1 edges in the spanning tree of n vertices. Hence, this is a graph of 8 vertices. Hence, any spanning tree of this particular graph will have 7 edges, isn't it? Now, somehow we have to find the minimum spanning tree of this particular graph. So, we have to select 7 edges intelligently, which will give us the minimum spanning tree, or we have to discard some of the edges in this graph, so that we remain with the minimum spanning tree. The Kruskal algorithm says this: if you have got any graph, say we will take our old example only. So, we are given that we are trying to find out what is the minimum spanning tree of this particular graph. Then Kruskal algorithm says like this: for this particular graph, first plot the forest of all vertices. What is the forest of all vertices? Say if it is V1, V2, V3, V4. Forest of all these vertices, 0 edge means just plot them, don't put any edge. Don't put any edge on them. I am just, this is the algorithm. Okay, what they say is that if you got a graph of n vertices, then first plot a forest of n vertices with 0 edges. It will be looking like this. This is a forest, isn't it? Because it is having a disconnected graph in which each subgraph is a cycle, in which each subgraph doesn't have cycle. So this is a subgraph, this is a subgraph, this is a subgraph, and nobody is having cycles in it. Hence we call this a forest by the very definition of the forest. It doesn't have any edge. Now what it advocates is, now just put all these edges in the increasing order of their costs. What I mean, first this edge V1, V2 will be there, that is because it is having the minimum edge 2, then 5 will be there, then 6 will be the minimum weighted edge, then 8 will be the minimum weighted edge, then 9 will be the minimum weighted edge. Put all the edges in the increasing order of their costs. So what you do, V1, V2, first you put this guy because this is having the minimum weight, then V2, V3, this is the next minimum weighted edge, then V3, V1, that is the next minimum weighted edge because it is having 3 as its weight, 6 as its weight, then V1, V4, this is the next minimum weighted edge, then finally V3, V4, that is the next minimum weighted edge. So it says that arrange your edges in the increasing order of their cost. This is the order that you get. You have arranged the edges in the increasing order of their cost. Then take the first edge and put it in this particular forest that you have considered, you constructed some time back, and see by putting this particular edge, check whether you are forming a cycle in this particular forest. If you are forming a cycle, don't put this edge, otherwise put this particular edge. Now let us check. By putting V1, V2, of course it will not form any cycle because it doesn't have any other edges inside that. Hence this doesn't form any cycle. So I put this V1, V2 there. Then I will take the next weighted edge, that is V2, V3. I will put this V2, V3 here, depending on the condition that whether V2, V3 is forming a cycle in this particular forest or not. When I put V2, V3, it is not forming any cycle. Hence I put this particular edge. Then V3 V1, I have to put this or not depending on the fact that V3 V1 is forming the cycle in this particular forest. When I put V3 V1, definitely this is like this is like this, and it is forming a cycle, hence I don't put V3 V1 into this particular forest, I ignore it. Then I will move on to the next minimum weighted edge, that is V1 V4. I will see whether V1 V4 is not forming the cycle or not, but when I put an edge like this, it is not forming a cycle, hence I consider this. And then V3 V4 I attempted to put, when I put V3 V4 it is forming a cycle, hence I don't put it. That is how I check all the edges, whether I have to put it in the forest or not. If it is not forming the cycle, I will put it, otherwise I don't put it. Hence the algorithm says that this guy is going to be, is definitely the is definitely a minimum spanning tree. Okay, we will see this animation and get a better understanding of this particular algorithm. Now tell me, what is the forest of all these guys? This is the forest of all this graph. Then consider the edges in the ascending order. What is the edge that is having the minimum weight? This particular edge is having minimum weight of all. So I will try to put this guy. If it is not forming a cycle, definitely I can put, because this is not forming cycle. Putting an edge like this is not going to form the cycle, hence I put it. Then after 2, what is the minimum weighted edge in this particular graph? 3. So when I put 3 here, when put this edge in the forest, it is not forming the cycle, hence I put that, I put 3 there. Then what after 3, what is the next weighted edge? 4. Next minimum weighted edge 4. I'll put 3 4, the edge called 3 4, because it is not forming cycle, I can put it. What is the next weighted minimum weighted edge? That is 6. I will put it because it is not forming the cycle. What is the next weighted edge? 7. 7 I will put it because it is not forming the cycle. Now what is the next weighted edge? That is 1 3, having the weight 8. Now let me see if 1 8, can I put it here or not? Can I put an edge called 1 3 in this particular forest? If I put an edge like this, I will be getting a cycle, that is 1 3 2, that is a cycle. So I don't put the edge called 1 3, I just ignore it. I don't put it. I don't put the edge 1 3 because it is forming a cycle. Then what is the next weighted edge? 9. Can I put 9 over here? I can't put 9 because it is also forming a cycle with 2 3 4. The resultant cycle will be 2 3 4, hence I don't put even this guy. What is the next weighted edge? That is 3 5, I put it. The next weighted edge happens to be a 3 6, but it is forming a cycle like this. If I select this, this forms a cycle like this, this will be a cycle, hence I don't put that particular edge, I just ignore it. So the next weighted edge happens to be 14, I will put it, and then that is how I covered all the edges, and hence I will stop the algorithm and say that this is going to be, this is a minimum spanning tree. In fact, here only one trick you need to observe. You can actually check this whether edge is forming the cycle business or not till all the edges are exhausted, or whether this particular tree is having n minus 1 edges. Whichever is earlier, you can stop it there. In fact, n minus 1 edges will always be coming earlier than the seeing all the edges satisfy this particular property or not. Soon after you get n minus 1 edges here in the spanning tree that you are trying to generate, you can terminate your algorithm. and if you see this cost is 2 plus 7 plus 4 plus 10 plus 6 plus 3 plus 14, which is nothing but 46. Hence this guy is going to be a minimum spanning tree of this particular graph that we have got. And if you ask me, sir, is it the only minimum spanning tree, or can we have many minimum spanning trees? I can comment like this. In fact, there is a theorem, there is a famous theorem which in fact which proves us that if the weights of all the edges are distinct, then the minimum spanning tree is going to be unique. If any two edges have the same weight, then the minimum spanning tree need not be unique, may not be unique. So when you know all the edges are distinct, all the edges have got distinct weights, then for sure you know that it is going to be a the spanning tree that you get will be the unique minimum spanning tree. You will not get any other minimum spanning tree. This property, this particular thing depends actually on whether your weights are distinct or not. Your weights are distinct, you know that the minimum spanning tree is unique, otherwise you can't say. The theorem that we can prove actually can find in books where you can find this particular proof of the theorem that we spoke. In this case, if you ask me, sir, is it going to be unique or not, this minimum spanning tree that we have got, I'll ask the question, all the weights are the weights of this spanning of this graph are distinct, weights of edges of this graph is unique. Yes, they are unique because none of the weight is being repeated, hence this is going to be the minimum spanning tree of the graph that was given to us. This is what is Kruskal algorithm. Basically this algorithm, backbone of this algorithm is an algorithmic technique called greedy approach. This is called a algorithmic technique. It says that you always try to select the best possible option that is available at that point of time. This is a technique actually. You probably study this technique called greedy approach in algorithms course, maybe in the next semester or so. Then you will be able to appreciate what greedy technique is, and in Kruskal algorithm only that particular technique has been exploited. Okay. So next let us see the Prim's algorithm. It says that you start with any vertex. You're given a graph, so you start with probably any vertex, and at each step you add an edge to the spanning tree that you would like to construct, satisfying some conditions that we speak. And when we have got all n vertices covered in spanning tree, probably you can stop the algorithm and say that is the minimum spanning tree. And how to select an edge in a step is what we speak now. Say we'll take, you don't worry about it, I'll just be with me. So let us consider our old graph that we have been studying, old example that we have been studying. This is 2, this is 5, this is 9, this is 6, and this is 8, and this is a 6. This is 6. So this is V1, V2, V3, V4. So we have got a graph, then it says that you consider basically two sets S and A. S is the set of vertices and A is the set of edges. The first vertex, you probably take any vertex for that matter, no problem. Say in our example we will take S as say V1. Then what I do is, how many edges are going from V1? This particular edge is going from V1, this particular edge is going from V1, this particular edge is going from V1. There are 3 edges that are going from V1, isn't it? Then find out who is the edge that is having minimum weight. Probably V1 comma V2 is having minimum weight, that is 2. So now what you do is you increase this particular set S by V2 and put this particular edge V1 V2 into A. So this is the first step. Now what is your S? S is this portion is called S, and what is the edge set that you have got is V1 V2. This is now first step is being done. I will do this n number of times, and finally whatever the edges that are going to be there in A are going to be the edges of my minimum spanning tree. What is the next step is, now what is the set S? V1 V2. Now look at all the edges that are going from the set S. This is one edge that is going out of S. This is another edge that is going out of S. This is another edge that is going out of S. This guy, this guy, this guy. Among these 3 edges, find out the edge which is having minimum weight. In our case it happens to be 5, isn't it? 8, 6, 5. 5 is the minimum weighted edge. Minimum weighted edge. So take this particular vertex, that is V3, into your S. In this particular step, now S becomes V1 comma V2 comma V3. This is your S, and put this particular edge also. Put this particular edge, because 5 is the minimum among 8, 6, 5. Put the edge of V2 V3 in A. Now A becomes V1 V2, one edge, and the new edge we are going to add is V2 V3. This is another edge that we are going to add now. Now S is having 3 vertices and your edge set is having two edges, that is V1 V2 and V2 V3. In the next, the second step is being done now. In the third step, what is the S now? S is V1 V2 V3, isn't it? This is my current S, V1 V2 V3. Now look at the edges which are going away from S. What are the edges that are going from S? 8 and 9, V1 V4 and V3 V4. Among these 2 edges which is having minimum weight, V1 V4 is having minimum weight. Hence add V4 to S and add V1 V4 to the edge set A. Now S becomes V1 V2 V3 V4 and A becomes V1 comma V2 V2 comma V3, and this will be V1 comma V4. This is the edge that we are going to add now, isn't it? Because among these 2 this is having the lesser weight. At this point of time we will stop, simply because we have covered probably all the vertices V1 V2 V3 V4. We don't have to go any further. Now if you ask me what is the minimum spanning tree, I will say it is this. I will look at this edge set and I will construct it. V1 V2 and V2 V3 and V1 V4 is the minimum spanning tree, and of course you can easily verify that 2, 5, 8, this is going to be the minimum spanning tree of the graph that we were given. This is what this particular algorithm is about. We will do with an animated example and conclude it. Now take the same example that we have seen for Kruskal's algorithm. So now select any vertex. Probably I am starting with the vertex 5. Now in this vertex 5, what are the edges that are going out of 5? 5, 8, 5, 6, 5, 3 and 5, 7 are the edges that are going from 5. Out of these 3, who is having the minimum weight? 5, 6 is having the minimum weight, hence add 5, 6. Now your S becomes this guy, isn't it? S becomes this. Now S becomes this. Now what are the edges that are going from S? This is one, that is 5 comma 7, another one is 5 comma 3, another one is 6 comma 3. Among these 3 edges, which is the edge that is having minimum weight? Of course 10. So you add 3 to S and this edge 3 comma 5 to A. Now your S is this. Out of these S, how many edges are going out? That is 3 comma 1, 3 comma 2, 3 comma 4, 5 comma 7. Among these, what is the edge there with the minimum weight? 3 comma 4. Hence put 4 into S and select 3, 4 into your edge set of the spanning tree. Now consider this as S. How many edges are going away from it? 3 comma 1, 3 comma 7, 4 comma 2 and 5 comma 7. Among these, which is having the minimum weight? Definitely 2 comma 3 is having the minimum weight. Hence put 2 into S and select the edge 2 comma 3 into your set S, that is the edges of the spanning tree. This is what the resultant thing is. Then you can continue like this and finally you can find this as the minimum spanning tree. And this algorithm is also basically is a result of the approach, the greedy approach. Greedy approach is a technique to solve problems, and this algorithm is also basically built on that particular technique called the greedy technique. And thus we have seen couple of algorithms to find out a minimum spanning tree of the given graph. And we have seen that if the weights of the graph or weights of edges of the graph are distinct, then the minimum spanning tree is going to be unique. Okay, and a lot of practical problems can be modeled as graphs, and by finding minimum spanning tree most of the problems will be solved. So the way that you model the problem is very important there. Okay, with this we conclude this session of finding the minimum spanning tree of a given graph. Okay, thank you, bye.